So we're trying to come up with what the acceleration and the velocity vectors would look like for this ladybug that's rotating in a circle. I want you to think about objects that we know that move in a circle, and some of the easiest ones to think of are the Earth moves in a circular orbit that was air quoted around the sun, and the moon moves in a circular orbit around us. If I were to ask you to draw a free body diagram for that ladybug, or like a free body diagram for the moon, how would you draw it? What would you do? Would it matter what position it is in the circle? What if we stopped it and we said, okay, draw a free body diagram right now? What would you do? If that was the moon orbiting the Earth and the Earth is in the center, let's pretend the Earth is in the center and this is the moon. Ignore the size, I know they're different. If this was the Earth and this was the moon, what would you do, Tiho? No, think of that. I want you to think of that ladybug as the moon and the Earth is in the center. What would you draw? Will? Yeah. Force of gravity towards the Earth, right? Is there anything else acting on the moon? Yeah, there's lots of other forces of gravity, but the reason that the moon's in orbit is the FG coming from the Earth that's acting on the moon, right? Kyle?
Is there a normal force?
No, nothing is supporting it. Yeah. So, hey, gang, what does that mean? That means the moon is free falling towards the Earth. We are free falling towards the sun. We're free falling towards the center of the Milky Way galaxy. That's what that means. Kyle?
Does that mean that we're slowly being pulled closer?
Yeah.
What you're basically saying?
That's basically what I'm saying. It's nuts. We're gonna die. No, don't worry. It takes a long time. When you're only falling at what's the moon falling at? It's experiencing our acceleration due to gravity, 9.8 meters per second squared, right? So that's not very much for given the distance that it is. Like, think of how far away it is, how much area how much distance it would actually have to cover to fall and crash into us. That's definitely not going to happen in humanity's lifetime. Right? We got bigger things to worry about, not the moon crashing into us. We got way bigger things. Okay? So that's nuts, right? To think that there is, if you were drawing a free body diagram, and I'm going to just put something on here so that we can see what we're doing. You can't see it. I'm going to show you in a second. Don't worry. If I was doing a free body diagram for the ladybug, I would just say that the force that's acting on the ladybug is the force of gravity, just Fg, right? What if I let the ladybug go to the top of the circle? Now what? What's your Fg towards what? Yeah, towards the center of the circle. Okay, so the moon is orbiting the Earth in a circular path, and it's doing that because of the force of gravity. Okay, that means it is free falling. That means that our F net, wow, let's think about this. The F net, is it always in the same direction? We can say towards the center of the circle to make it sound like it's the same. The acceleration is towards the center of the circle. Is the velocity, here we go, is the velocity towards the center of the circle? No, which way is the velocity? Justin? Yeah, perpendicular to the acceleration. What's that word? Tangential? Am I using that right? If we show both vectors here, there goes the ladybug. So the acceleration, I'm going to draw it on here. You're drawing it on yours as well. The acceleration is towards the center of the circle. That is the acceleration. It's a centripetal acceleration. So it's an acceleration that keeps things moving towards the center of the circle. And the velocity, look at the velocity vector. It's the same size all the time. But what's different about the velocity? Sydney?
Changes depending on where it's at.
Right. It's changing direction, right? So I would say the speed is the same because the speed doesn't care about direction, but the velocity of anything that's in orbit, anything that's doing this circular motion is changing. The value, the size of it, the magnitude is the same, but the direction is changing every single, I don't know what you want to call it, every single moment of interval of time or whatever, because we've got this tangential to the curve, right? It's that velocity is actually tangential to the curve. I'm going to draw that perpendicular. That is the velocity. The position vector is right over here in the bottom right. Can you see that? Yeah. The position vector is right over here. So you can see that the position is trying to move towards the center there. Cool. Okay, so that explains, like, that's what we're looking at. And we're going to use this information and move to our next unit on gravitational fields. We're actually going to think about all of the stuff that we're learning right now. So this is a massive care into what we do next. Oops, I really meant to erase that. I'm glad you guys can't see that. Okay. So we're taking a look at what's happening with the ladybug. I want you to flip to the next page and take a look at, I'll give this ladybug a rest here. Pause. Take a look. Switching over. There we go. Nice. Suppose the ladybug crawled in concentric circles, like in figure below. Draw what you think the velocity vectors would look like at the location shown in figure 2. So you don't have to do, since we've already figured this out, you don't have to do figure 2 and then make corrections in figure 3. Just pick one of them, one of the spots to draw your actual answers, right? So what we want to identify is that the velocity vectors at each of those points are, just like we said, tangential to the curve. That's the velocity. Glad I can lift the iPad and turn it. Whoops. Except I missed. Come on. Don't know why I'm missing. Wow, I should just give up. Maybe I really can't do it upside down. So the velocity vectors all the same size, but they are, oh, that doesn't look perpendicular. You can make sure that each one of them is perpendicular. Yeah, those are your velocity vectors. The acceleration vectors, I'm going to put them on the second diagram. That makes sense. The acceleration vectors are all towards the center. That's what keeps the object moving in the circle, is all towards the center. Okay, so I'm going to write that down. Is perpendicular to acceleration. And the acceleration is towards the center of the circle. So we're just going to kind of summarize where this equation is coming from. I'm going to try and simplify it in a way that might make a little bit of sense here. Okay, so the acceleration around a circle, when an object accelerates, its velocity is changing. Because velocity is a vector quantity, acceleration occurs whenever the speed or the direction of an object change. Thus, your car accelerates at speeds as it speeds up from a stoplight or as it turns a corner. In a similar manner, the Earth is constantly accelerating. See, this is the thing that wows people. Constantly accelerating as it orbits the sun because its direction is constantly changing. The acceleration of a turning or orbiting object is known as the centripetal acceleration, And the force responsible for this acceleration is the centripetal force. And that's the force that's actually pushing inwards to the circle. If you're in that frame of reference, though, if you're in the accelerating frame of reference, do you feel the push into the center of the circle? No. What do you feel? You feel opposite. Think of yourself as on the merry-go-round. Think of yourself on those rides that move in a circle. You feel the opposite, out of the circle push. That's the fictitious force because you're in the accelerating frame. Ooh, it's all coming together now. Isn't this exciting? The big thing that we do want to remember is that the centripetal force is made up of forces we already know. Do I want to say made up? Supported by, caused by, supplied by. I like supplies by. Supplied by forces we already know. Like tension or friction. Friction is what keeps your car on the road around a curve. Right? Think of like how you can like go really, really fast. No, you're not supposed to. You're supposed to drive really properly, right? But you can go fast around a turn in the summer, but in the winter, what happens? Do people make it around those turns as easily? No, they end up in the snowbanks off the road because the force of friction is actually minimal, which means it's not enough. It's not enough to supply the centripetal force that would be required to keep the car on the road. Okay, so friction can be contribute to the centripetal force. It can supply the centripetal force. Tension, gravity, the normal force. Just some examples of what can supply the centripetal force. So it's not like it's a new force. I think we want to make that clear. It's not a new force. We're just identifying what's happening in the circle now. So what we're going to do is we're going to look at the circle that's happening here. And we're going to assume, I'm going to say that the circumference of these circles that are on your page here, we'll say the circumference is 60 meters to make some numbers make sense here. So if the circumference is 60 meters, that means we can calculate the radius, right? Because we know the circumference is equal to 2 pi r. So I can say the radius, I'm going to calculate that out, because I cannot do this in my head. I can't divide pi in my head. Come on. 60 divided by 2 divided by... Just give me a second to find pi on this phone. Okay. Woo! I'm getting 9.55-ish meters. Okay? Is the radius. Okay, so if we are to cover sorry, Kyle?
How did you get these values?
I just made them up.
Oh, okay.
Yep, they didn't come from anywhere special. I totally just made them up. I'm going to say this circumference is 60 meters. Just made it up. Totally random. It's not like it's something that's constant. Thanks for asking, just in case. You probably weren't the only one who's confused there. So what I'm going to do is try and show you that we can come up with an approximation for the acceleration by minimizing the time interval that's required to complete the circle. So we look at a full circle to travel from, switch to red, travel from, let's say this is the start, to go around there, full circle. That distance is actually 2 pi r. That's the circumference. We're gonna say that the time to take that, hypothetical, I'm just making up numbers here. The time to do that circle is 12 seconds. That's just what it is. So what would you normally do for that? You would say, in order to calculate that, you could do the distance 2 pi r over the time to actually get your speed. But what's your velocity? Velocity is displacement over time. So what's my velocity there? Velocity is 0, right? Okay, let's take a look at why our velocity could be 0 here. If we had, using our equations of to get the velocity, we could say displacement over time, but we know that we're going to have objects accelerate, so we want to try and use our acceleration equations too. So let's say at the beginning of, I'm going to make this bigger so that this makes sense. And honestly, you're not responsible for knowing how to prove this equation. I'm just trying to give you a way that you have so you can try and understand where the equation's coming from. That's what I'm doing. If this kind of feels like it goes completely, you know, doesn't do much for you, it's okay, as long as you're okay with using the equation that we're going to come up with. So what's happening, if we look at an initial velocity, let's say originally the object has a v1 of 5 meters per second at the beginning of the circle. And then when it comes back around, its v2 is the same. It's moving at 5 meters per second. The value is the same. Remember, think of the ladybug, the velocity vector. That value was the same for when it was moving around in the circle, but the direction is what changed, right? So when we complete a complete circle, our v1 is at the beginning of the circle, our v2 is at the end of the circle. They're both 5 meters per second, and guess what? They're both in the same direction, right? So when we calculate acceleration and we say acceleration is v2 minus v1 over t, I'm going to put in v2 is 5 meters per second, v1 is 5 meters per second. So I'm going to go 5 minus 5 gives me an acceleration of 0 meters per second squared. Does that make sense? Are you kind of with me? Because it feels a little bit bonkers because I'm just making up these numbers. I'm totally just making up these numbers so you've got a context. Okay? So far, so good? All right? So just think about that velocity vector. It's only changing direction. It's not changing size. It's only changing direction, that velocity vector you saw with the ladybug. Okay, let's look at half a circle. If we look at from here to there, let's look at v1, and we'll keep v1 is 5 meters per second. We'll stay with our 5 meters per second. Again, the size is not changing, so our v2 is still going to be 5 meters per second, but we're halfway through the circle. That's your v2. What can you say about that v2? Aaron?
They're opposite directions.
They're in different directions, aren't they? They're in different directions. So when we calculate A, in order to get A, we're going to have to say, well, delta V, there's a spot here to write this. Delta V is actually going to be 5 meters per second. You can do this either way. Minus negative 5 all over the time, which is 6 seconds for half of a circle. So you're going to get 10 divided by 6, which is, wow, wake up here. You're like, what did you just do there? Sorry, I'm just calculating the delta V. That's what I wanted to do first. Just calculate the delta V. So to get the acceleration, what you're going to do is realize that your velocity is 10 meters per second. The acceleration would be 10 meters per second divided by 6 seconds, which is 1.6 seconds. 1.6 meters per second squared. All right. Did I confuse you there? Kyle?
I'm just wondering why one of the velocities are negative.
Yeah. Okay. So, because this one is to the right and this one is to the left. So they're in opposite directions. So I made this one positive and then this one's negative. And then, right, because it's halfway through the circle. So they're clearly in different directions. So, and it works out great because they're still coplanar though, right? One's to the left, one's to the right. They're still coplanar. So we can still subtract them nicely and not have to do any crazy math because they're still in the same plane. Okay. So far, so good. So our acceleration now, we can measure it using v2 minus v1 over delta t. Can measure it. It's about 1.6 meters per second squared. Now we get to the more complicated situations. Let's look at a quarter of the circle. If the full circle takes us 12 seconds, then a quarter of the circle will take us 3 seconds. Agreed? Does that sound about right? Our V1 is initially 5 meters per second. That's a 5. Our V1 is 5 meters per second. Our V2, whoa, is here. Perpendicular Guess what you're going to have to do with those vectors? Triangle, right? Triangle, right angle. The hypotenuse is your delta V. Okay? So 5 squared plus 5 squared, square rooted, so the square root of 57 something. 7 point, am I right?
7.07,
Thank you.
approximately.
Approximately. We're just having fun here anyways. So I take those two vectors, I make a vector diagram. The hypotenuse is the delta V, that's your resultant. To get the acceleration, I'm going to do delta V, 7.07 meters per second, divided by 3 seconds. And I'm going to get an answer of A equals 2.4 meters per second squared. T-Hill? Do the velocity again? Yeah. So see this vector here and this one? They're perpendicular to each other. So I'm going to pull them together and make a vector diagram so that you're actually looking at, I'm going to move this up just a bit, give myself some space. So what I'm doing is saying V1 is this way and V2 is like this. I'm solving for the hypotenuse. That's your delta V, okay? And that's where the 7.07 came from. Cool, glad you asked. Whoa, that's weird. Just here. Just stay there. That's a good spot for you. You don't want to stay there. Oh, boo. Don't worry about it, right? It's all, oh man. I don't know what the solution is. If you talk in a high, scary voice, things will work out. And I don't, is this the eraser? That looks like the highlighter. Now I can't even erase it, so we're stuck with it. Anyways, now you know where that came from. It's just written all over the place. Sorry, that's so awkward. Okay, so then the next one gets a little bit harder because you'd actually, instead of using nice Pythagorean theorem, guess what we're doing when we're at an eighth of the circle. If we're at an eighth of the circle, the time is 1.5. We're looking at the velocity that's here. This is your V1, meters per second. And your V2, perpendicular, 5 meters per second. They are not coplanar at all. So you end up with this situation where you're going to have to use some sine law, cosine law, you can put them together and get a triangle. What I'm saying is that you can actually calculate the delta V. We're just going to skip by that in order to save a little bit of time. The delta V is going to be something like that, which means our acceleration would be 3.83 meters per second all over 1.5 seconds, and you would get about 2.5 meters per second squared. So the big thing here is that we estimate the acceleration with less and less time in each case. Okay, we're estimating it with less and less time. As the delta t approaches 0, the estimate actually gets better. So when delta t equals 0, the acceleration can be determined by this equation. So it actually involves like using a little bit of the sine law, cosine law, lumping them together, using some fancy math, and you come up with this equation, which is all that you need to be responsible for. You do not need to be responsible for the proofs. I just kind of wanted to show you that, hey, we can build an acceleration out of this. We come up with the new equation. I'm run out of because I messed that up. We come up with a new equation. The centripetal acceleration is going to be related to v, velocity squared, over the radius. And that comes from using some fancy, it's like applications of the arc and stuff like that you probably haven't really even covered in math yet. but it's our relationship between the delta V and the delta T. We can actually realize that we can substitute the sides. We can look at the sides and look at the angle and make sure that we have an approximate value for what's happening there. Kyle?
Sorry, how did you solve for delta V
For the last one, it would have been using like the sine law or the cosine law. Yeah.
and where would you get that angle?
The because it's 360 degrees, and it's 1/8 of it. Yeah. Which apparently I don't want to do in my head right now. Embarrassing. Okay, so this is our equation for centripetal acceleration. And if you feel like I didn't really care for anything that you just said, that's really okay. All I really care is that you know that the centripetal acceleration is v squared over r. It's related to the velocity and the radius. So that radius, the circle's radius really is going to matter here. So you've got to be given information about the circumference or the radius in order to get anywhere. Okay? All right, let's see what's next. Yes. All right, so I've got your little report card things I've got to fill out, which I can do really quickly. You're going to work on completing this sheet. You're going to draw some free body diagrams. Do them all for the inertial frame first. Remember the inertial frame, do you remember this from before the March break? This is from the ground's perspective. The non-inertial frame is in the accelerating frame. Remember that awesome movie we watched? You can always rewatch it on YouTube. Just Google frames of reference video. What I want you to do is take a look at, these are all situations that you could encounter where frames of reference matter, and some of them are actually in circles. We really want to try and identify what is supplying the force that's required to keep something in motion. The cool thing about centripetal acceleration is that if we look at what we know F net to be, we know F net is equal to MA. Oh, I haven't done any attendance all day either. That's really good. We know that Newton's second law, F net, is MA. So I'm going to say, I want you to realize that when we're finding the centripetal force, which is obviously supplied, causes the centripetal acceleration, we can identify what the F net is because the A that you're substituting in here is no longer a linear acceleration. It is a centripetal acceleration. So that's how we come up with this kind of statement that the centripetal force can actually be related to mass times acceleration. That's actually in a circle. But that centripetal force isn't necessarily just one force. It could be made up of a couple. So that's why I prefer to leave it as the F net. I prefer to leave it as F net. Let's put this in brackets. Because remember, that F net really means the sum of all the forces. And the sum of all the forces that are involved are what's supplying that centripetal acceleration. Okay, so I want you to answer these 4 questions. Try and come up with good free body diagrams for inertial frames, non-inertial frames. We'll take it up before you go.
All your attendance for the day, and then you supply teachers, could you please bring down attendance sheets to the main office? Thank you.
We'll take that up before you go. How are we for the first one? So between the inertial and the non-inertial frame, that's from the ground's perspective, respectively, and the accelerating frame, respectively. What you're trying to do is recognize in the inertial frame, you could have an F net if there's an acceleration, right? So if there's an acceleration, that F net from the seat in the first example is equal to, the Fn from the seat is equal to F net. So you can see that where I state my applying Newton's second law. So I'm identifying that the vertical forces are equal. There's no acceleration in that direction, but there is an acceleration in the horizontal direction, and that's supplied by the back of the seat, okay? In the accelerating frame, if you're in that car, you see yourself at rest relative to the car, right? Are you moving in the car? No, but the car is moving. So we have got to find a way to satisfy Newton's laws to make sense of that, because the object is accelerating, but you are at rest relative to the object. So we want to satisfy Newton's laws. We create a fictitious force. That's where we write F fict. F fict. It's balancing the Fn of the seat. And if you're conscientious of that, you'll realize that the F fictitious actually just ends up being F net, but the acceleration's in the opposite direction. Okay, like, because they're both going to, the values of Fn of the seat are going to both be the same in both frames of reference. The thing is that the F fictitious is in the opposite direction. Kyle?
Do we have to use FN of the seat as opposed to, let's say, applied force?
Well, what would be the applied force then?
The bus. Like on the body, I guess.
But it's really the contact between, like, you're in a seat, right? So we want to identify the forces for what they actually are. That's a contact force. So if it's a contact, our normal force is how we identify it. Was there another question about that? Does that feel good? We can get there. So it's like we're trying in the non-inertial frame, we're trying to balance. Why do we feel at rest when we're in the accelerating frame? Because you are at rest, but you feel a fictitious force. A fictitious force balances you out. Tiho? Yeah. The fictitious force? The Fn in the seat pushes you, like, keeps you moving in the direction of the acceleration of the car. So, right, so the force applied is actually probably from the engine, right? The applied force from the engine. It's delivered to you via the support of the seat. Does that make sense? Yeah. Okay. And then when you're in the accelerated frame of reference, you feel the push back. That's the fictitious because you're accelerating. No, not in that case. It's not delivered directly to you. It's on the car, right? If you do a free body diagram for the car, FA, for sure. Yeah. Julia? You could add friction in there, yeah. So if you added friction, then that means your fictitious force would be smaller in your accelerated frame because you'd have friction and the fictitious balancing the Fn of the seat. Yeah. So far, so good? Josh?
Could I use F imaginary instead of F
Yeah.
fictitious?
Yeah. Elevator, this is a good one. This is, like, I love this because it really hammers home the idea of why you actually feel heavier in the elevator, right? So easy to do from the inertial frame of reference. You're good at this. A lot of us may have written FT because you're thinking of the tension of the cable, but guess what? The cable's not acting on you. I hope it's not acting on you. You've got the normal force of the elevator is what actually supports you. So if you're accelerating upwards and your velocity is upwards, you're speeding up, we better have Fn greater than Fg. So we say F net equals Fn minus Fg. Good. Let's go to the accelerated frame of reference. From your perspective, you're at rest. You are not moving relative to the elevator. So that means that there's got to be a fictitious force. And there is. That's why you feel heavier when that happens. That is, your Fn is actually greater, but you feel heavier because there's a fictitious force that makes you feel heavier, right? We're creating a force, and that probably didn't come out right. We're creating a force to explain why we get a certain feeling when we're in the accelerated frame of reference. Because when we're in the accelerated frame of reference, it feels like Newton's laws don't stand up, okay? They don't hold as true. So we want to make them hold as true because absolutely, both frames of reference will agree on Fg, right? They'll both, there's no reason for Fg to change, right? And they'll both agree on Fn. So we've got to have an additional force added in there. It's like I don't want to write the F twice. You've got to have an additional force added in there in the accelerated frame to make you at rest. So is that becoming clear? That you're taking, this is showing something that's accelerating. This is showing something that's accelerating from the ground's perspective. From the perspective inside the accelerating object, the person or object is at rest, right? So we want to actually create a force that balances it. So there is no acceleration. Does that make sense? Okay. Wicked. Next slide. And okay, good. Fingers crossed that worked. Sorry, your sheet does not look as nice as mine. The printers are just nutso sometimes. Okay, so Swinging the bucket, thank you for, Emma, you had this right originally, and then I told you, oh no, fix it. It's actually, if we were drawing a free body diagram for the bucket, there would of course be tension, but it's not. It's for the water inside the bucket. So you're drawing a free body diagram for the bucket, not for the bucket, just joking. You're drawing a free body diagram for the water, and it's moving in a circle, and that's the free body diagram for it. It's at the top of the circle, and I think the question clarified that. Yeah. Swinging, yep, at the top of the circle. Thomas? Yeah, so there'd be normal forces. They'd be probably pretty tiny. Like you mean the contact forces coming from the container? So 2 sideways ones and a downwards one? Yeah, you could do that if you want, yeah. The reason that they're contributing very little to the centripetal, right? The big contributor is the FG. Mark?
When we have these types of free body diagrams, when things are swinging in circles, do we always assume that the velocity is constant?
The velocity isn't constant. The speed is. The velocity is changing direction, right? The magnitude of the velocity is. Yeah. And you're not assuming. We know that it's moving in a circle, that it's going to be the same. The size of it, the direction is what's changing.
Why is there nothing pushing to the side?
Pushing to, what do you mean?
The water.
Well, that's what Thomas just asked. He said there would be some normal forces containing, yeah, you could draw some little normal forces on both sides and from the bottom of the bucket. You could draw those on if you wanted to. But that's not the reason why it's moving in the circle. The reason it's moving in the circle is because of the FG. So the FG is supplying its centripetal motion. Yeah. So when we look at that free body diagram, before you even knew about centripetal motion or centripetal acceleration, you would just write F net equals FG, right? But now that we know that things are moving in a circle, we can say, hey, FG is supplying the centripetal force. Okay? Was there another question? How much time?
So if we're like looking at the bucket at that point, would all the water be like pushed to the side, like the direction would be pulled around? Is that
Because if we pull away the gravity, then it would go tangential, yeah. So it might look like that. I don't know, we should try it. We should try it tomorrow. Let's try it. See if we can actually capture that somehow. Okay, and then of course there's an F fictitious that balances that. Last one. 2 children holding hands moving in a circle. Our F net is going to equal the force of tension there. So I can also say that the force of tension is what is supplying the FC, the centripetal force. And then, of course, the kids in the circle, they actually feel a push outwards of the circle, right? They feel it out of the opposite direction of where the acceleration actually goes. How's that seem? Okay, so tonight for homework, you're doing lesson 10's homework, which should be centripetal acceleration. It's just using A equals V squared over R. Nice and easy, you'll love it. A equals V squared over R. That's what your homework is on for tonight. Tomorrow we'll do more on the centripetal force, and we'll show you what banked curves actually looks like, so you can get ready for that practice test on Friday. Good job. We will finish off centripetal force stuff tomorrow. Objects moving in a circle, they experience a centripetal acceleration, and we know that acceleration is V squared over R. So it's related to the velocity of the rotating object and the size of the radius. We know that forces cause acceleration, so it only makes sense that the cause of the centripetal acceleration is the centripetal force. But the centripetal force is not a force all on its own. And that's often like the biggest misconception people make. They're like, well, what is the centripetal force? We don't want to identify it as its own thing. It can be one force or it can be a combination of forces. And like we said yesterday, it likely is a combination of forces you already know, like the gravitational force or tension, friction, and the normal force. Those can all contribute together to actually provide a centripetal force. So your centripetal force, think of it almost like F net in a circle. The F net, the forces that are interacting, that is happening in a circle. So we're going to look at this situation. It's kind of like a roller coaster. This is like this used to be a thing in a circus. People would hop on bikes and go around in a loop. And it was like very exciting because, woo, they don't fall to the ground at the top of the loop. And how do they stay in the loop? And really, as you just saw in the videos, it's actually all just physics. That should be your answer for everything. It is all just physics. So what we've got here is we're going to identify what's happening to the driver of this bike as they complete the loop. The performer has just enough, okay, that matters, just enough constant speed. So this means minimum speed that would be required to get the object through the circle, okay? Because if you're moving a bit faster than the minimum speed, life is going to be a little bit easier. Then that's usually what's happening with roller coasters, right? Like you saw even in the video that the roller coasters, once you're pulled up by that chain, you're just on that track. Chain's gone. That is all conservation of energy and forces that are keeping you on the track and moving still, right? So in this example, we're specifically looking at having just enough constant speed to stay in the circle and stay on the track. And we want to look at the free body diagrams in each of the situations. So what's happening from the top, bottom, right side, and left side. Okay, so let's give it a try. Because this is really key. I'll erase that. Okay, from the top, our circus performer. What do you think? What are the forces that would be acting on the circus performer up at the top? Any ideas? What's the easiest one, Kyle? Gravity. Yeah, like when in doubt, put gravity, right? Gravity just can't disappear, so definitely gravity. Anything else? Josh?
Force forwards.
What do you mean?
Like he's riding on a bike, so there has to be force pushing him forwards.
He's accelerating like there's an acceleration to the center of the circle, but we're just at the minimum speed. It does say constant, doesn't it? He's just enough. So this is the minimum speed required to get through it. So would we draw a horizontal? No. Okay. Anything else that you want to draw in there? I'm just trying to trick you. You don't want to draw a normal force? Why don't you want to draw a normal force? That's interesting. Why don't you want to? You're right. Why don't you want to? Mohammed? Hassan?
Technically speaking, he's falling towards the center of the circle. So the ramp isn't really very aerodynamic because it's not pushing on the
Oh, that's a good explanation. Way to go, buddy. That's awesome. It's very different. The minimum speed is actually key here. The minimum speed tells us that there's just enough speed for the circus performer to move through this complete circle. So that's going to be key. You're going to look for that in the questions, because if it's moving beyond the minimum speed, there would be a normal force. Okay, that's pushing back. I love how Mohammed Hassan identified that it's just enough. Technically, the circus performer is in free fall towards the center of the circle because of gravity. Okay, so it's almost like without that Fn, there could be a brief, tiny moment that the performer leaves the track. Does that make sense? And that's happening at minimum speed or minimum velocity, okay? So that's the only time that would matter. I'm going to write that down here, where we're going to say that our F net here is actually equal to our FG. And I would say, therefore, FC equals FG. At minimum velocity. No Fn needed to stay on the track. So I'm just going to jot this down just so you can have it if you need it. The object may leave the track. For an instant. Cool. Mohammed Hassan?
So in this case, is your velocity scale perpendicular to your acceleration?
Yeah. still perpendicular. Good question. So far, so good? Let's do the bottom one next, because that's the next easiest, I think. I think the top and bottom are easy, but maybe not. There we go. Okay, bottom. What do you think? Still FG, right? Can't go away. Uh-oh. FG is not pointing towards the center of the circle. Uh-oh. What is? Connor? You betcha. And it's going to be bigger than FG. So, this is what's happening. F net, just like you would do normally, this is not any different than what you would do normally, right? You would see that Fn is going to be greater. We're going to have an acceleration towards the center of the circle. That's what's keeping, just like the video said, that's what's keeping the object in the circle. So there has to be an acceleration towards the center. But just looking at that free body diagram, you would normally write F net equals Fn minus Fg, right? You would totally do that, okay? In this case, our F net is your FC, right? So you see how FC is just F net but in a circle? So the combination of the normal force and gravity are providing the centripetal force here. See how it's not just one force? It's a combination. It's the interaction of these forces. The other way you can think of this, if you don't even have to write the FC, you can go straight from F net. If you prefer that you don't even have to introduce what FC is. You can go straight from this and say, well, I know that that's mass times acceleration, but that acceleration is centripetal. Okay? And then you've got a formula for AC. It's V squared over R. So we're building up how we can actually do problems like this using centripetal motion. How are we so far? Is this okay? All right, so there's an F net towards the center of the circle. We would identify that as the centripetal force, but like I said, you can just call it F net, but with a centripetal acceleration if you'd rather not bring in FC at all. Okay, let's try the right side. Which way is this guy moving? All right, what do you think? Down the ramp? It's moving counterclockwise, right? Is that correct? Thank you. Sorry. Thank you. Yeah, going toward, yeah, gotcha. Thank you. Well, as soon as I heard left, I got myself confused, but I'm okay now. Don't worry about it. Everything is okay. On the right side, oops, I'm going to leave. I should stay in the same color. On the right side. Okay, what forces are acting on the right side? Oh, yeah, let's do gravity. Thank goodness. Okay, gravity, good. Gravity, yep. What else? Mark?
Force normal pushing towards center.
Yeah, totally. So I can draw that to the left. Is that correct?
Yes.
Okay, thank you.
Is Fn also written FG in this case?
Sorry?
Is Fn also written FG in this case?
That FN?
Yes.
That one's the one that's towards the center of the circle, right? So does it look, like if you look at that picture, would that thing stay in a circle? Does it look like it would stay in a circle? What do you think? What? Yeah.
Like there, and it just goes like that.
Right, totally, right? And what if we want to do multiple loops? We've got to have what do I want to say? I want to have this be the force that's controlling that motion, right?
Please enter all your attendance for the day, and any supply or on-call teachers, could I please have attendance sheets?
Is there a way we can balance FG? Aaron?
Would it be FA from the person biking?
Yeah, totally, right? On the right-hand side, is he coming down the ramp?
Yeah. Going down the ramp.
On this side?
He goes on the right side, he goes down, he goes around, and he comes
back down the loop.
Okay, so I'm going to say friction for braking coming down. Does that make sense? To balance the FG?
FG goes down with their rate.
Right.
It could just be the friction from his tires.
Yeah.
The
Sure.
friction from his tires. Trying to find the force.
Because this object is moving down, right?
Yeah, it's moving downward.
On the right-hand side, is it moving down? Like that?
Yeah, because
Down and around?
going down this ramp.
Okay, so what I'm trying to say is that we want a force to actually balance gravity there, because we want to be able to say that our F net towards the center of the circle is actually supplied by Fn. Agreed? Does that seem reasonable? Okay, so on the other side, going up, what do you think? Might have to do a little bit of pedaling. Pedal, pedal, pedal. Still gravity down. My arrows are getting wonky. Fn towards the center. There's got to be something here. Fa. And I think this actually, it's like you have to, how do I want to frame this? If you're going at the minimum velocity, it was just enough to keep you on the track. So that means that on your way back up, if you were at the minimum velocity, you're going to have to pedal a little bit more to overcome the force of gravity that was pulling down on you if you want to stay in the circle. Does that make sense? Right? Okay. But if you're beyond the minimum velocity, you don't need to, right? And that's how those roller coasters are working, right? Because they're beyond the minimum velocity, that the Fn is great enough that it's so dominant to keep the acceleration towards the center of the circle. Does that make sense? Yep, Kyle agrees with me. That's good. How about the rest of you? How do you feel? So I'm like, this is like the biker pedaling. Does pedaling have 2 D's or 2 L's? It looks funny. Amy?
I was just wondering if FA is equal to FG or is it greater than?
I'd say it's equal to. At the minimum velocity, I'd say it's equal. Yeah. So that way we keep the acceleration towards the center of the circle. Okay? Which we should write that down. Thank you, Amy. You're right. So far, so good. Are you okay? All right. So this minimum velocity really matters. The sideways ones are really hard. The ones on the right and the left side are harder free body diagrams to do. The top and the bottom are a little bit easier for us. But remember that top free body diagram would change if the object is moving faster than the minimum velocity. There we go. Next page. Let's try some practice. All right. Looks like we got a rock on a string here. Marie is going to swing a rock in a vertical circle at a constant speed, okay? The rock reaches the lowest point in its trip, and Emmy says, I can feel the string pulling down on my hand. There must be a net force downwards. Isaac says, I think I can feel the forces. I think at the bottom, the forces balance. Albert says, it's a lot of people, since the object is moving to the left at this moment, the net force must be to the left. Who do you agree with and why? Think about that for a bit. I am going to draw my velocity vector. They just said it was moving to the left. Which way is the acceleration? It's perpendicular to that, right? Well, I always like to draw a free body diagram wherever I can to make sense of something like this, right? I'm going to draw a free body diagram, and I'm going to say, FG is down. What else? Erin? FT, yep. And is it going to be greater? Yeah. So we would say our F net, or our centripetal force, would be equal to FT minus FG. Okay, what do we think about the comments these people made? Emmy says, I can feel the string pulling down on my hand. What is she identifying? Mark?
Force of gravity.
Yeah, she's identifying that, like that pull, that she's actually experiencing that non-inertial frame, right? That she can feel that pull, that outwards pull, right? So she's identifying that. Albert, what about Albert? Albert says, since the object is moving to the left at this moment, the net force must be to the left. What do you think about Albert's comment? Let's be nice to Albert. He's like completely wrong, right? But he is recognizing that the velocity is tangential, so we'll give him that, because it would be obvious that at that moment in time, if they were to let go, whoever's spinning, Marie, if she were to let go, that it would actually move tangential. It would move off to the left, right? So, in this explanation, we can say centripetal force caused by Ft and Fg Emmy is in that non-inertial frame. Albert is recognizing velocity is tangential. Okay, so let's look at it at the top of the circle. Swinging the rock around at the top of the circle. Fg is still down. Where's tension now? It's down, right? Right, it's obvious that tension is down. What do you think is going to happen to that tension vector? What do you think? Compared to what we had at the bottom, we had this at the bottom, Fg down, and then we said the tension was bigger. Because it's got to be greater than gravity in order to keep it in the circle, right? What do you think's happening to the tension now? Thomas?
So the difference between it's like subtracting the points of gravity, but it's like smaller.
It's smaller, right? So at the bottom, we would say F net is equal to Ft minus F, whoops. Save. Yeah. Ft minus Fg. But at the top, our F net is going to be equal to Ft plus Fg. So think about that. The radius is the same. The velocity is the same. So the acceleration is the same the whole way through, which means your F net is the same the entire way through. Fg can't change because you didn't change the mass and we didn't move to a different planet. So what's the force that's changing? Sydney? Yeah, it has to be tension, right? Because the other ones cannot change. F net isn't changing because those F nets are dependent on mass times acceleration, right? And that mass times acceleration, you could expand that even further to be mass times v squared, which we were told is constant, over r. So if the v and the r aren't changing and the mass isn't changing, then F net's constant. It has to be tension. Tension's got to be smaller. But again, I should have got the buckets out so we could try this. I want to do that at some point, so you can actually feel it. But when you're spinning something in a vertical circle, you'll notice that if you're just at the minimum speed, you'll almost feel the object in free fall for just a tiny, tiny moment of time. You'll feel the object almost free fall a bit because it's almost like the tension isn't even there. It's just kind of like, it's just gravity that's actually keeping it in the circle, okay? So at that minimum speed, the tension, just like with the biker on the track, the FN wasn't there, the tension goes away completely. The rope would go slack. It would go a little bit slack, and it's almost like you could kind of almost see the object, the rock, kind of free fall a little bit because the V isn't great enough beyond that minimum velocity. Okay, so the force that's changing is actually the tension. Ft is changing. Okay. This is just a top view of a rock sitting on like a record player, and it's moving around, and it stays in the circle. It's a top view, so it's almost like it's a bird's eye view, so you're not going to show the FN or the FG, right? You're looking at it like at a bird's eye view. From a bird's eye view, this thing is moving to the right. That's clockwise, right? It's moving clockwise. What's keeping the rock moving with the disc or the record? What's keeping it? How is it not flying off? Kyle? Yeah, totally. It's the friction between the two surfaces, right? So in a situation like this, you draw a free body diagram, force of friction. So that means F net equals the force of friction. Which then you can say that FC is supplying your force of friction. The force of friction is actually supplying the centripetal force. So any circular motion, we want to keep that in mind. Any circular motion requires that there is a net force towards the center of the circle. And you just got to figure out what force or forces are working together to make that happen. Last one. Sorry, yours didn't print out very nicely. The ball in the funnel. You've seen these kind of things before where like you can drop a penny into the inside and it goes round, around, around, around. Stays at the same spot for a while. Tio? Sorry? It's just so it's just friction is the only thing. It's like sitting on it's a rock sitting on a rotating disc, and the disc is rotating, and the rock's going to rotate with it. And the reason it's rotating with it and not flying off is because there's friction between the two surfaces. Does that make sense? So friction, and this is the same kind of thing that keeps us on roads. When the roads get icy or they get wet, we lose friction and we might not be able to complete the turn. But for the most part, any kind of turn, think of that the next time you drive around a bend, anytime you're driving around a curve like that, there is a center of that half curve, and it's actually friction that's keeping you towards the center of the circle. It's not your wicked awesome driving skills. You're so disappointed, aren't you? Okay, so this is one of these. We have one of these at the Ontario Science Centre. Haven't been in there in ages, but there's an exhibit where you can actually drop the marble, and the marble rolls and rolls in a funnel. It glides around in a horizontal circle with no vertical motion. So you've seen those kind of like Make-A-Wish miracle ones where you drop a penny in and eventually goes down. That's because the gravity has got to be greater. This one at the Science Centre has it completely balanced so that it just looks like it would go forever and ever, and you have to actually reach in and take the marble out to get it to stop, because gravity doesn't pull it down. So we want to try and figure out what's going on here to make this object look like it's going in a circle. And if I am drawing a free body, I'm going to draw 2 free body diagrams because look, this thing's at an angle. If I'm looking at this marble, I'm going to say FG down. And then there's another force. What is it? No. What do you think it is? It's sitting on something. So what does it have to be? Justin? It's the normal force, right? It's the normal force perpendicular to the surface, right? Like that one, right? Good old FN. So FN, boom. Yeah. Is FN pointing towards the center of the circle? No. It's not, right? Is the center of the circle up in that direction? No. The center of the circle is like right here, right? Huh. So Fn can't be supplying the centripetal force. What could be? What do you do if you saw a free body diagram like that? What would you do to that diagram?
Get there, right? Triangle.
You betcha. We'd resolve that thing, right? We'd resolve it, and you'd end up, whoops, with an FG down, an FN vertical. Yo, that's totally balancing FG, right? That would explain why it's not sliding, it doesn't have any vertical motion, because FNV is totally balancing FG. And then there would be the horizontal component of that, FNH. So in this situation, we would actually say FNV is equal to FG, no vertical motion, but our FNH is your F net. Oh, I'm like out of control there. Which means that FNH is your centripetal force. Take that a little bit further. Mass times acceleration, just for fun. Because this is what you're going to do when you actually start solving things with numbers. AC is V squared over R. So it's actually the horizontal component of the normal force that causes the circular motion. You're probably tired and you probably don't want to do the banked curved one, do you?
Is that on the practice test?
It's the exact same as the funnel. Yeah. But we can go through the proof for it. I'm going to take the bank curve one off. It doesn't matter to me. Let's do it. Let's see if we can do it, because we didn't resolve this properly. So let's move on to the bank curve, and because you can actually see how it breaks down really nicely. So this is a perfect example, perfect segue into the bank curve, and I hope I have that slide next. Yes, friends, last one. Pushing your brain. We're pushing your brain, which is probably super tired. Okay, so banked curves. We've talked about very briefly, we've talked about like how your car will stay on a road as it goes around a turn. But sometimes there isn't enough friction that will actually keep you in that center, right? Won't keep you with the acceleration towards the center. So on a non-banked curve, we would normally have the friction that's between your tires and the road. It would supply the necessary centripetal force. But what if there's no friction? And that happens a lot, especially in environments like us, where half of our year we could be covered in snow and ice. How do road engineers, how do civil engineers solve this problem? That we've got to make sure people aren't driving off the side of the road and ending up in the ditch all the time. They bank the curve. So they're just elevating the curve up. so that the normal force, the horizontal component of the normal force, will actually step in and supply the necessary centripetal force that's required to keep the car on towards that center of the circle. So what you're looking at over here is like a bird's eye kind of view of a car going in a circle. And we know that the motion is that way, that's the velocity. Our acceleration is this way. If the acceleration is that way, then that means that you've got a centripetal force that's causing that, right? So that's the point of that. This is the velocity. This is your direction of your centripetal acceleration. When things are moving in a circle without any incline, friction would be supplying that centripetal force. Oh, shoot, sorry. On a non-banked curve, friction supplies it. Satellites, FG, sorry, I just gave it away. Force, the centripetal force is supplied by gravity. For a yo-yo, the centripetal force is supplied by tension in the string and gravity. So what we can do is we can really use that angle that the incline actually banks at to help us figure out what the horizontal component of the normal force is. So I'm going to focus on this truck here. And you can see that for that truck, you would want to draw a free body diagram that's got FG down and that there is a normal force that is perpendicular to the surface, right? The thing is that the normal force can't be providing the centripetal force itself because it's actually not pointing towards the center of the circle. So we want to figure out what's pointing towards the center of the circle. We want the force that's actually here along this plane. We can get that if we resolve the normal force. And if we resolve the normal force, we're going to feel a lot better about there's no vertical motion then, because the vertical component of the normal force will balance gravity, right? So that's how you're not slipping up and down the ramp. You can actually stay along the corner. You can stay at the exact same spot around it because there's no vertical motion because the FNV, the vertical component of the normal force, is balanced by FG. Okay, so by banking the curve, by raising up the road, the car is given an FNH that is actually towards the center of the circle. Listen, I'm really busy. I'm going to number the steps so you can see what I'm doing. So the first thing we're looking at is basically you've got a car on an incline, right? And we've got FG down just like you normally would, even if it weren't moving in a circle, and FN perpendicular to the surface. That is not different than what you're used to doing. The biggest mistake that students will make here is that they'll try and resolve FG. You can't resolve FG. Why can't we resolve FG for this question? Adam? Yeah, we can get the mass. But why can't we resolve FG for what's happening in this situation? Why does it have to be FN? Aaron?
If you resolve the G, you would have a force like pointing towards the center.
Awesome. If I resolve FG, where is that horizontal or the parallel component of gravity going to point? Down the incline, right? So I don't want to touch FG. I want to balance FG out so that we're not having any vertical motion at all. So we've got to resolve FN. And we're going to resolve FN. Make this bigger. Nope, I'll do it in its own. We've got to resolve FN. So let's say FN looks like this. It's got an FN vertical. and an FN horizontal. Make that big so you can see it. There's your theta. Maybe that Z pattern is actually easier to see. So we can find a value for FNH, right? We can find a value because we know that FNV will be equal to FG. Which is equal to mg. So I can say the tan of theta is going to be equal to FNH oops, sorry. I'm going to put over mg there. The opposite, let me label my triangle. I didn't do it. H, O, A. So I've got FNH is the opposite, and FNV, which is equal to mg, is the adjacent. So I can now say that FNH is equal to mg tan theta. So this becomes really, really straightforward because these kinds of questions that you get, oh yeah, you're going to run out of time. Do I have an answer? Oh, I do have an answer on this one. So in a situation where it's a banked curve question, this is a good example. It's an icy road. We're going to assume no friction. Friction's off the table. It can't be providing the centripetal acceleration. We want to calculate the maximum speed possible if the bank is if the road is banked at 15 degrees and the radius of curvature is 65 meters. So watch what you've got here. You've got FNH equals mg tan theta. If you've drawn a free body diagram for that already, you can say that FG is balanced by FN vertical and FN horizontal points towards the center of the circle. We want to find the maximum speed. So this is what we're going to do. We're going to say F net. Oh, stop. We're going to say F net is equal to FNH. F net is MAC. And FNH is mg tan theta. Cancel out those m's. Good. Gone. What's A? It's V squared over R. Now you can find that velocity, can't you? Because you've got the radius, you know the banking angle, and you know acceleration due to gravity. That's it. That's all that there is to the banked curved questions. Identify the force that's applying the centripetal force towards the center. It's the normal force, the horizontal component of the normal force. Once you've got that, you're setting up this situation here. You put those numbers in and you will get 13.1 meters per second. You did it. Way to go. So practice test tomorrow, going to be a good indicator for what you're going to see on Tuesday. You're going to try your best, even if that means that you're just doing a couple of questions, right?